This is going to be a bumper video on the latest vision language models. I'm going to start off by giving you my recommendations on the best model to choose, whether you want a small, fast model or a large, high quality model. Then I'm going to spend time going through Moondream, which has released an updated version. I'll show you some of the specific features, including gaze recognition. After that, I'm going to go through SmolVLM. They have released some even smaller versions of their vision language model, which are powerful and also small in size. Then the main part of this video, the third part, is going to involve a live run through of me fine-tuning Qwen 2.5 VL. Qwen is a new series of models released, the 2.5 series, that actually outperforms some of OpenAI and Claude Sonnet's vision models. This should be particularly instructive if you're trying to fine-tune a vision language model or you're trying to figure out what the strongest available model is for your given application. So here are my recommendations. If you want a model that is small and you want to run it on device, I still think the Florence 2 model encoder decoder style is the highest quality in terms of the answers that it gives. There are also a SmolVLM as a model. There are two sizes there, and there's the Moondream model, and those are good alternatives. Moondream additionally provides the ability to do gaze recognition. So I'll go through each of those models, but actually I still think Florence 2 is the best in terms of performance, both raw and after fine-tuning. Now, if you're trying to optimize for quality and you want something, you're willing to go for something a bit larger, then Qwen, the Qwen series of models 2.5, which has just been released, is definitely the way to go. They now have a 3 billion parameter model, a 7 billion, and a 72 billion parameter model. And these just tend to outperform all of the other models that are out there, including now some of the private models. So I'll go through some of the features of that model and talk through in detail how to fine-tune it. Actually, I'll fine-tune it live. I'll be updating a previous script so that it works and is compatible with Qwen 2.5 VL. So to get started, let's look at this latest Moondream release from January 2025. And there are a few updates here. The first is that you can prompt Moondream to give you structured outputs. I'll be testing that out in an Inference notebook. The second improvement here is around gaze detection. So you can see Lionel Messi here, and Moondream has detected that he's looking at a ball. Moondream has improved in terms of performance, so it's up there around Qwen 2. Now Qwen 2.5 is just out, so actually this has moved up on the chart. And here it's showing as significantly better than PolyGemma and SmolVLM. Well, SmolVLM has significantly improved since then and is up there in this similar region as well. That's a model that has come out in smaller form, even smaller form earlier this year, and I'll be going through fine-tuning of that too after Moondream. OCR has improved on Moondream as well, better at reading text in images, and those are the four main updates for now. So I'm going to focus on Inference with Moondream because it is a versatile model in terms of the different features it can do for inference, like object detection or structured outputs or gaze detection. It is more tricky to fine-tune, and that's why I recommend fine-tuning instead maybe Qwen, or to fine-tune the Florence 2 model, or to fine-tune the SmolVLM model. So to look at inference, I've put together a custom notebook. It's available in the advanced inference repo for those who would like to buy access. You can go to trellis.com/advanced vision. Now, I'll hopefully describe through all the scripts, so even if you aren't in a position to purchase, you should be able to figure out how to hack together a lot of this for yourself. Now, I've git cloned the repo and I have it here in Cursor. Let me close down my tabs to simplify this a little bit. And you'll see this repo contains a wide variety of scripts. There are data preparation scripts if you want to fine-tune models. Those are covered in detail in my video on Lava, which is now somewhat older and deprecated, but the data preparation remains much the same. Then I have fine-tuning scripts for Florence 2. I have a whole video on that, which I point you towards if you want to understand bounding box detection and object detection. That is quite a detailed video that goes through everything there. There are also scripts here for fine-tuning diffusion models, which is outside the scope of this video. And then for fine-tuning Edifix models, now older and deprecated, Llama 2 Vision, Pixtral, Lava, the older Moondream, Qwen VL, which includes now Qwen 2.5. I'm just going to upload the script today, actually, so it'll be ready. It's the last part of this video. And also scripts for fine-tuning SmolVLM. But now I'm going to start by talking about Moondream, and I'm going to go to the Moondream 2 folder and open up this Moondream 2 inference. I'm going to run this notebook locally, and to do that, I'm going to make sure that I'm in my correct folder. So I need to be in Advanced Vision, and I further need to be in the Moondream 2 folder, and I further need to activate the correct virtual environment. Now, this is actually within the fine-tune folder. So I'll go into fine-tune and then Moondream 2, and I'm going to do UVVenv, which should activate a virtual environment. And now I can select that virtual environment. In fact, it's already selected here, and I'm ready to start running the notebook. Now, just a few heads ups here. If you're going to run Moondream, I'm running it on device here on my MacBook. You can also run it in Colab by uploading this notebook if you like. I'm doing some installations you might expect, like transformers. I need to install Torch, PyTorch. If you're running on an instance like Colab, it'll have PyTorch already installed. Same if you're running on a Jupyter notebook in RunPod. I'm installing INOPS, Accelerate, HF Transfer for fast weight downloads, and Matplotlib for some graphing later. But something I should mention is that you should ensure that not only do you have Torch installed if you're running locally, but you also install PyVips. This should be necessary if you're going to run locally. Now, I'm going to enable HF Transfer. This allows for fast weight downloads. It's not that crucial because the weights are quite small. And then I'm going to load the model here using Auto Model for Causal. So it's fully compatible in terms of loading here. It's just tricky to fine tune because the data collation is not obvious how to set up. I'll go through data collation for SmolVLM and for Qwen later on. But yeah, it has changed throughout time as well for Moondream, which makes it just a little bit trickier to find. Note that Moondream uses revisions. So even though it's the same repo, the model can update even in architecture over time. So make sure that you have your revision pinned right here. You'll also need, I think, to set trust remote code. Not entirely sure if that's needed, but if you run into issues without it, try it. It gives permission to run Python scripts within the repo. Now I've set my device to MPS for Mac. You can set it to CUDA or to CPU, depending on your device. And I'm going to load that model and I'll print it out. Now, the Moondream model is a combination of a vision model plus a large language model with a connector. So once we've loaded the model, which took 8 seconds, we'll be able to print it and see indeed it's a vision model, followed by 2 fully connected layers, 2 linear layers, and then a text model that's truncated for ease of visualization here. Now, I'm going to pass in an image. So for this, I'm going to just show you how to run a few of the inference capabilities of Moondream. I'll show you how to get a caption, how to get a long caption, how to do pointing to an object, how to do gaze detection, how to do structured outputs. So bear with me, there's a fair amount to cover here. The first thing I'm going to do is just open up an image. It's an image I've created. I don't actually remember how I created it, maybe with ChatGPT, but it's this woman and this man looking at each other happily, perhaps lovingly, and I'm going to use that as a basis for a gaze because I want to find the line of gaze between the two. Let's start though with a short caption, which is done using Moondream and model.caption. This is a custom Moondream library function. And the short caption here, which takes on Mac 5 seconds, a man in a blue tunic and a woman in a yellow dress with green hair. So a fairly short caption here, serene expression. Can also go for a normal length caption, which is streaming. I think it's streaming. It's maybe streaming faster than I'm able to move. And yeah, in a forest setting, the man with the long hair and a beard, they're facing each other, their gazes lock. And so yeah, it seems like it has given me out here the caption and streamed it. And once the streaming is done, it's printing out the final option here, the final object, just because I've set it up this way to print out that full caption. So working very well. We can next ask a question of the image. So caption will just generate a description, but you can also talk with the image by using model.query. For example, how many people are in the image? And it should tell me, yeah, there's 2. Next, we have that structured response. So I'm going to ask for XML. And when I run that, I get an XML type response describing how many people are in the image, not just a woman, but her hair, clothing, expression, etc. So you could also do YAML. You could do JSON as well. Now we're going to move to visualizing objects. So we're going to first of all figure out how to find in an image the faces, and then we're going to find how to find the gaze for a face. And in between then, we're also going to find out, which is an independent feature, how to point at certain objects. So to do this, object detection, we'll use model detect, and I wrap this in a visualize object function. And my goal is going to be visualize faces. So I've set the object type to face. And then I've set up a simple function that allows me to plot those. And you can see here, it's able to correctly identify the faces. Very accurately, I would say. Next is visualizing points, and this uses model.point. It's very similar to finding objects, except that it's going to point to a certain type of thing, one of which can be a person. And yeah, it's just put an X here in the middle of each person. Now, we can first use the model.detect to find faces. And once we have the location of the faces, we can pass that to a gaze function, which will allow us to find what that face is gazing at. So you can see in the visualize I'm first detecting the face. And then when I have the face, I'm able to pass that into model.detect gaze. So I pass in the image and the face center. And the face center is just calculated as the midpoint of the face, the rectangle for the face. Now there is more code here. This is just for processing the face and then for making sure I can plot the face and plot the gaze. And when I run that, indeed, it works out nicely. And this is just an image I generated, so I haven't done any fine tuning. I even tried it out on an image of me looking at my computer. This is some weeks ago, checking out my main screen. And let's see how the gaze is. Here's my face, here's the gaze. And let's check me looking at the side computer. Here's my face and here's the gaze. So this looks pretty nice. I think it's a great feature. If you're looking for something like detecting soccer players, sports players, maybe safety during driving, you want to see where the driver is looking, for example. Maybe you want to see safety for kids, you want to see where they're looking. Different applications like this, I think the gaze detection is a very useful feature. So that rounds up Moondream. As I said before, I'm not going to go through fine-tuning just because the compatibility is not great as of now. I believe Moondream will release some fine-tuning scripts. I'll add that to the description once it comes out. In the meantime, I'm going to focus on the fine-tuning of SmolVLM, which is compatible with Hugging Face transformers. And also then I'll show you Qwen 2.5, which is also compatible. And I'll go through those two scripts in detail right now. And next up, we have SmolVLM. Now, SmolVLM already existed, but there are even smaller versions available now of 250 million parameters and 500 million parameters. That's smaller. It's roughly around the size of the base Florence 2 model, or smaller than the large Florence 2, which, even though called large, is only 700 million parameters. So these are all small models. Now, there are a few updates with the SmolVLM architecture and how they train it. So I'll quickly go through those, and then I'm going to show you how to fine-tune SmolVLM. There are comparisons here, and unfortunately, it doesn't compare exactly how the performance is against other models, but they do compare against Edifix ADB from 17 months ago, and really the comparison is just smashing. So we're even doubling the performance with a 500 or even 250 million parameter model compared to an 80 billion parameter model from 17 months ago. So a few things about these SmolVLM. It uses a smaller encoder. These models, all that I'm talking about today, they have two parts plus a joining part. They have a vision encoder, and then they have a language model, an LLM, and there's a connector in between, usually an MLP. So the encoder, typically people would use a clip type model, and the model that's being used here by SmolVLM is actually a smaller version than historically would have been used, but it's been found in ablations by Hugging Face that basically they weren't really getting much improvement by using the larger model, so the smaller one sufficed. Now this is good because obviously it makes the model faster, and it also makes it smaller in terms of VRAM required. The other things that are changed are using what's called pixel mixing. Now this is a technique that it kind of is appearing in different formats across different models right now. I'll try briefly explain it. There's a version of it that's used in Moondream as well. It involves appending along the channel dimension instead of along the sequence dimension, and that saves you basically in the effective number of tokens that you have as an input. The easiest way to show that is, let me go to a PowerPoint slide I have. You can see here, this is what I described just a moment ago. Typically you have a vision encoder and you have a large language model, and then you have an adapter that basically converts the vision tokens into tokens that are acceptable by the LLM. And this vision encoder, if you kind of zoom in, what it does is it takes patches from the image. Here I've got 4 patches, and it will embed each of the patches separately and then send them through a neural network, which is also a transformer model, to produce then some embeddings that would be fed into an adapter, an MLP layer, and then into the LLM. Now, it's become popular with this kind of pixel mixing, or depending on the channel dimension, it's become popular instead of actually taking all 4 of these vectors, one for each of these patches, to just concatenate each of those vectors essentially and treat it as one token. So you have a larger dimension because you're concatenating these 4, let's say, but you have fewer tokens. And this is advantageous from an inference standpoint because the inference usually will be slowed by having a long sequence length, which means lots of tokens. So if you can append along the channel dimension, it turns out you end up not degrading quality too much, but you get a significant speed up. Now, pixel mixing is a little bit more complicated than that because it follows more of a structure in exactly how you append. But it's broadly speaking, I think, the same category of technique that's used in Moondream, and this allows them to reduce the memory requirements of running the model. This is not a trick that's used in Florence 2. So there is that benefit in terms of speed for these SmolVLM models. Okay, so what else do we have on the SmolVLM side? I've shown the results. Here you can see the throughput. It's showing the throughput of 2 different models. And this is the number of examples processed per second. So you're actually able to process multiple examples per second, although this would be with a batch size, which if you're running inference on device, you may just have a batch 1 anyway. So you're really only inferencing at the low batch size. I've pretty much covered everything. There's one small update on the data mixture. So compared to the previous release, there's basically a reduction here in the OCR amount, an increase in the OCR amount of data. You can see that orange. It's a bit misleading because it goes both ways, but it goes from 25% up to 41%. So this is the biggest change and is aimed to improve the document comprehension understanding of the model. So I'm going to go through now how to fine-tune this model. Again, I'm going to use the advanced inference repo, and I've put the scripts into the SmolVLM folder here in this Python notebook. Now, you could run this, again, if you like, locally. That's perfectly fine. Or you can run it on a GPU. I'm actually going to run the training this time on a GPU, which will be a little bit faster. And to do that, I'm going to use a one-click template from the one-click LLMs repo. I'll put a link below. This is a public repo, and you can just search for a fine-tuning notebook. So here we have a run pod, one-click notebook. I'll click on that. And now I'll open up a GPU. I'll just use an A40, and I will, here you can see the template is selected, and I'll deploy that. And once it's up and running, I'm going to upload my my notebook so that I'll be able to run training. And the training I'm going to run on is on, you'll have guessed it if you saw some of my videos before, it's on fine-tuning on a chess set. So to detect chess pieces, actually I have at home here, I took photos of them. If you want to understand the data preparation, there are scripts in this repo that you can use for doing the data prep. And it's in the data prep folder here. I point you towards the Lava video if you want to figure out that a little bit more for yourself. So my service is starting up. I'll open the Jupyter Notebook, and I'll now just upload the Jupyter Notebook. Okay, so I've uploaded the notebook, and I'm going to do some of the typical installations. So I'll upgrade pip, install transformers. I'll install PEFT, parameter efficient fine-tuning, so we can do LoRa fine-tuning. We're not going to fine-tune the full matrices in the model. We're going to fine-tune some smaller adapters that will plug on to the model. So that'll save VRAM. And optionally, you can train this in quantized form if you install bits and bytes and set up quantization below. Now, if you want to push your model to hub, you can log into Hugging Face. I'm not going to bother with that for now. I will set this environment variable just to make sure we have fast downloads through HF transfer. And now I'm going to load the model. You can see here I can load either the 500M or the 256. And I'm going to load the 500M, which is the slightly larger model, and it should perform a little bit better. Now it seems we have some issue here. Okay, I'm not entirely sure why I hit the issue with FlashAttention, but I've just installed one of the previous versions and fixed it there. So you should be able to install that from the script. All right, so now we're going to download the model. As I said, we're going to run with a larger model here, and we're going to pick a device of CUDA. You could also run on MPS if you want to use Mac, or you could run on CPU, although it will be slower. Now, if you want to use quantization, this is the configuration to pass in by uncommenting quantization configuration here. The attention implementation we'll use is FlashAttention 2 if the device is on CUDA. Otherwise, we're going to use eager. So if you're on, say, CPU, or if you're on Mac, then you're going to use eager attention. And we're going to use bfloat16. If you're going to use this in Collab, then you should change it to float16 because the T4s, those GPUs don't support it. So we download the model there. And optionally then you can run the model to check a few images and see what the kind of results are. So I'll actually run that just to show a demo. The model is about 1 gigabyte in size. That's because it's 500 million parameters, and in 16 bits, that means 2 bytes for 16 bits, which makes it 2 times 500 is about a gigabyte. Now we'll see here 4 different images: a dog, mountains, the seaside, and a path. And we're asking the assistant to describe it. And here we go. Let's see, foreground. Yeah, it doesn't really see the dog here. Basically, if you pass in 4 images to the model, it's gonna typically struggle in my experience. Whereas if you pass in just 1 image, let's pass this in like this, and I actually need to adjust the number of image tokens being passed in as well. And actually that helps me just display 1. And you can see here, it's performing well when you just pass in 1 image. So yeah, already SmolVLM, I think if you try pass in multiple images, it's probably going to be challenged, but it does very well if you just pass in 1 image. Next, we're going to test the formatting. So I should say that the SmolVLM models are trained in the same way as Edifix. I've done Edifix videos before, so it's pretty much the same format as Edifix 2 or Edifix 3. It involves setting up the text in a form of messages like this, and then you can put in the text in the content as type text, and you put in the image as type image, and then you will pass the images in, you will see, to prepare the inputs. So we'll see that a bit later. But for now, I just want to print out the chat template, and you can see when I apply the chat template, which is taken from the processor that I've loaded back up here. So when I loaded the model, I also loaded the processor. You can see it here, which contains the tokenizer. It's called a processor because it's got to process both images and it's got to tokenize the text. That's why it's not just called a tokenizer. So you can see the format. We have IAMStart user, we've got a question, then we have a specific token for the image, then we've got end of utterance, then we've got assistant. This is a chessboard with pieces, end of utterance, and then user with a new question here. So you can see that end of utterance basically follows every single turn in this format. So with the model loaded, we're going to move to fine tuning. To do that, we're going to train on a data set of chess pieces, and I'll load a data set here and I'll run evaluation just so you can see it. Actually, I won't run it, but I'll just show you the results. So here, for example, we have a bishop and a knight, and you can see it recognizes it's a chess piece, but it doesn't, it says a chess piece, so that's incorrect. And it doesn't mention the type of pieces. Here we have 2 bishops and a rook, and it says a close-up shot of a white, brown, and cream chess piece on a light wood table. So broadly correct, but not very specific. And likewise here, it says a light wood table with 3 pieces in the background, which is not exactly right either. So we're going to see now if we can improve that performance using fine-tuning. And there is a sample here for running on multiple images, but as I said, SmolVLM is poor in my experience running on those. You can run evaluation here as well to test out the OCR. So I've tested it out on this Financial Times page just to see what kind of headlines. It should definitely pick out this court freezes Moan assets. And yeah, indeed, it does pick out that main claim, but generally a stronger model will pick out many more of the headlines as well. Even Florence 2 will pick out more of the headlines. So it's clearly accurate in picking out that main headline, but not so accurate in pulling out more than that. So with that kind of capability illustrated, we'll move to the training loop. Now, the typical way you'll see online in many examples for training is to train and apply the loss over all of the user input and the response. So that means when you're calculating the loss or the penalty you can think of between the prediction and what the models and what the ground truth is, you're considering both the question and the response. And this can be fine, particularly if you have long responses. But if you have short responses, that information in the response, which is really what you're trying to improve the fine tuning for, it kind of gets diluted. And so it can be better to actually focus the loss only on the responses and not focus on the accuracy of the model and predicting the question. Because in a real example, it's only ever going to have to predict the answer, not the question. So I've set up a data collator here, and it collates messages in this format. So we've messages with the user, with the question and the image being passed, and then the response, which is the assistant with a text-only answer. But you'll see that when we prepare a batch, we actually clone that batch to provide a set of labels. And the labels are the targets. These are the correct ground truths that we're trying to match. And then we mask the non-assistant tokens. So everything that is including the assistant kind of prefix and everything before we want to mask out. And the way we do that is by finding a hard-coded subsequence. And the hard-coded subsequence we're going to look for is going to be, the hard-coded subsequence, which is found here. And then, it's just found in this function. It's defined when we initialize the data collator. And I currently have set the hard-coded sequence to assistant. So / assistant, n, that's new line, and then assistant and the colon. So what we're doing is we're taking the collated prompt with the question, the image, the answer. We're looking for this / assistant. And when we find it, then we're going to mask everything, including it and before. And that's what's happening here. We're basically applying the masking, which is -100, which tells the loss calculator to ignore those tokens and just focus on the response. Now I'll do this again later on when I show you fine-tuning Qwen, so just keep that in mind. Okay, with that done, we'll just run it and we'll print out a sample batch. So I'm basically collating a batch of data. And what I want to do here, by the way, you can see that actually each image is represented by many, many image tokens. And there are many, many image tokens in row 1, column 1, row 1, column 2. So you can see essentially it's kind of like seeing the pixels of the image in a little bit. But importantly, what I want to check is that the masking is correct. So when I decode and I exclude any of the masked tokens, I just want to see the responses. And that's what I see, because I see a single white rook and I see a white rook here. So these are two decoded masked labels and they're looking good to me. So I'm happy that my collator is set up correctly. So next, I think I've got a simple inspection here. I'm just, again, double checking that the assistant response and the decoded labels are matching, which they are. And you can see here, I've set skip special tokens to true. That's just to hide any of the special tokens. If I run it, what will happen is they won't match just because the decoded labels will have these special tokens included. So they are truly there, but when you set that to true, it's just going to hide them. And that will result in an exact match now. So we basically have the data collated. We've got the loss focused on the results or on the responses. So we're ready to feed this in now to the trainer. But first, we need to set the model up with LoRa. LoRa is the low rank adapters that we're going to apply to the model. We're not going to train the main matrices. We're going to train these smaller adapters. And to decide which adapters to apply, which modules to apply the adapters to, we need to print out the model. And if you print out the model, you'll see SmolVLM is actually an Edifix 3 for a conditional generation model. It has a vision model with an encoder. It has a connector, which is a modality projection. It's an MLP layer. And actually, yeah, it is a simple MLP layer. And then we have the text model, which is a llama type model. So we're going to focus on training as much as we can. I usually like to do that if possible. You probably could only train the attention and be fine. But I'm doing that by setting the target modules to all linear. And furthermore, I'm actually training the raw matrices from the language model head and the embedding tokens. So that's kind of right at the start and the end of the language model. And the reason I'm doing that is it just gives some extra parameters that you can achieve a better fit with. It's technically most important if you're changing anything about the tokens and how tokens are used on average, and especially if you're adding in new tokens, which we're not. So it's not maybe essential in this case, but it just gives extra parameters. That's useful because it's already a small model. So that means when we use LoRa, we're not going to have many parameters that are being changed. So to kind of counteract that, you can just set more to being trainable. So I've defined my LoRa configuration. Here I'm going to get my model with LoRa. This function calculates the matrices for the adapters. And I'll print my trainable parameters. I think it'll be a high percentage of my total parameters, which now includes the model plus the adapter parameters. It's 20%. That's because I'm training at the language model head and the embeddings. And now I'm going to run a main training. And the way I like to run this training, it's a little bit manual, but I like to run it twice. So I like to run first with 2 epochs, and I have a relatively high learning rate because my model is small, so half times e to the minus 3. And I train at a constant learning rate for these 2 epochs. And then I like to do a small annealing. So I'll rerun all of this, but I'll rerun it only for maybe 0.4 of an epoch. You could rerun for another epoch. Really, I just want to run for, say, 100 steps. And I'll run at the same starting learning rate, but on a linear decline. So I'll have 2 epochs like this, and then a decline like this. So I've run like that, and you can trust that I've run that twice. And so here actually you're seeing the results from the second time I ran, which is just the annealing step. So I'm only running part of an epoch here. And yeah, you can see it's very fast. It's running 0.4 of an epoch in 30 seconds. And my validation loss is only falling a little bit here, but that's because I've basically done the constant and now I'm annealing. And so let's see now if we get better results. What do you see here? And we see a white queen and a white rook. So it's now giving answers that are in the format we want. It's seeing 2 pieces. It's seeing the right colors. It's not getting the pieces right. Here it's seeing a white queen. So this is a poor prediction. You could argue it's maybe seeing this, but it's certainly poor. And here it says a white rook and a black knight and a white pawn. So it's actually it's technically getting these. This, I think, is actually a pawn. So it is getting these 3 in this case. So overall, if I have to count correct pieces, I would say, ignoring this pawn, I'd say it's getting 2 pieces out of the total 7. By comparison, Florence, I think, is capable of getting 4 or 5, and the Qwen models I expect will get that or even better. So this is definitely a weaker model in terms of fine-tuning. And if you want to get accuracy on this data set, you would need to use quite a bit more data than what I have, which is about 40 images worth of fine-tuning. Now, when you're done, you can push to hub. Just merge the model first. That I would recommend, because then you can use the model easily with VLM for inference, and then push that model off to hub. So this here is your SmolVLM fine-tuning. Next up, I'm going to talk about this model that has just been released, Qwen 2.5 VL. It's the strongest open source model out there right now for vision. And in fact, it probably beats some of the private models on many of the metrics. You can see here, for general visual questioning answering, Qwen 2.5 VL is outperforming Sonnet, outperforming GPT-4o. Same on video understanding. Now, Qwen has put a lot of effort here into video understanding, something I'm not going to cover too much in this video. And then agents are also becoming very important. I probably will do a video on computer use. Let me know if that's of interest in the comments. But you can see Qwen are focusing on this and performing quite well, although some of the leading other models, they're not really being compared properly because there isn't data, or they're not intended exactly for video use yet, or rather for visual assistant use yet. Now, what else to say about Qwen? It's an improvement upon version 2. So this is moving to 2.5. It's got a few improvements it's calling out, like worldwide recognition, precise object grounding. I'm not sure object grounding was possible before. So now you have the capability of doing bounding boxes and even these sub-labels. So you've got a label and a sub-label. Furthermore, the improvement, there's been an improvement in the text recognition. So everybody working on OCR, and then document parsing, the ability to convert a PDF like this into HTML. So this is very nice because it means you can move that directly into an LLM, and it should be able to do some interpretation much more concisely, or rather much less data heavy than having to store this as an image and pass it into the LLM. As I mentioned, video is a big emphasis, and so is this visual agent part, which I'll plan to do a video on later. But for now, let's see how strong the Qwen model is. I have kept open my RunPod instance on the A40, and I'm just going to shut down the kernel for running SmolVLM. Shut down all the kernels actually. And I've uploaded a Python notebook, a Jupyter notebook for Qwen VL2. And I'm actually going to live work through this, so you'll see any mistakes that happen. I'm going to try and get the 3B model to work. So let me update the name of this notebook and we'll get started. So all of these things should be installed, but I'll just install again. Let's see if we get that FlashAttention error. It's possible we will. It seems like there's some bug with the latest version of FlashAttention. Notice how we are installing Qwen VL utils. That's going to help us out with fine tuning. Now I had no errors there, so I'll keep going. And I'm going to make sure we have fast download enabled. And I'm ready now to install, or rather download, the latest version of the model. Now let's see if that's actually the name. We will find out soon. Oh no, it's 3B. I think I was pretty close, not close enough. So there's the 3B, and then I think there's the 7B, and then I think there's the 72B. So I'll put all of those in there. And yeah, I don't know if Florence 2 will be stronger than this, so let's give it a chance. Now I'm going to load that in the same way as I did earlier. We're going to use FlashAttention. Sometimes that gives issues with Qwen, so let's see. The model is downloading here now, 2 shards. It's a 3B model, so we expect it to be about 3 times 2, 6, plus the vision model, which is probably small, so maybe 7 gigabytes. And yeah, it's about 4 and 4. It's about 7.5 gigabytes. Let's check out. I won't quite yet. Oh, we have an issue here. Let's see what this is. Could be the FlashAttention. Trying to set a tensor of shape in bias. And it seems to be to do with the device. So let's try uninstalling FlashAttention. Oops. And let's try loading with that equal to eager. So I'm actually just going to copy that. And I'm going to set it to eager for sure. So let's see how this goes. The download should already have happened. So we'll see now if it works. Ooh, interesting. Qwen 2.5. So that's maybe not recommended. Yeah, makes sense. We're not actually importing the correct model here. So let's check the right way to do this. And yeah, it looks like we need to install like this here. So let's go back to change this and change this. And you could argue this should not be here. You could argue I should maybe leave in FlashAttention. Let's see. Let's see if that gives issues. And we may also find that we need to change how we are formatting the prompts if there's a change from Qwen 2. And there may well be, because this now supports bounding boxes, for example. So we'll just have to see if that poses an issue or not. Yeah, and interestingly, it looks like we did have FlashAttention 2.7.3 installed. And that's probably because I didn't put the U flag there. So that actually is probably one of the reasons we may have had an issue. So we'll make sure to install this version. And we may still need to come back and uninstall it. But for now, let's run with this. And it can't import that from transformers. That's interesting. So that suggests that I do need to update my version of transformers. So let's try that. And now we'll try again. Now, sometimes what needs to happen is to restart the kernel. So we will restart the kernel. And we will try run this again. Okay. So maybe there's another package. And this just shows you I should have read the instructions fully. Okay, we may actually need to be on the dev version of transformers. And it says there's a specific recommendation if we're installing video. So let's uninstall transformers. And then let's install it with accelerate. I think I've installed accelerate already. Let's check up here. Yeah. And I can put in a queue here for people to use next time to save all of this. And it looks like that did install. And we will restart the kernel. and cross our fingers. Okay, so looks like that is loaded. And look at this. Wow, this is beautiful. So the max model length of this is 131,000 tokens. Very beautiful. But we're going to limit it because we don't want to run out of VRAM. Now, I may not need to limit it that much because it's just a 3B model. But yeah, I'm going to limit it. And actually, it's a bit misleading the way I've done it. So you can see here, yeah, if I ran that the first time, I should actually uncomment because it'll confuse people if they run it the first time. But yeah, basically what I'm doing here is I'm allowing the model to be limited in max length via the tokenizer to 4,000 tokens so we don't run out of VRAM later. And let's see how it handles these multiple images. And we'll again find out whether this is the format it expects, which it may or may not. Okay, wow. So this is pretty great. It's getting that correct. And let's have a look at the tokenizer. So I'm assuming the same as Qwen 2. Now I'll load the chess pieces and let's see the evaluation before training on the chess pieces. I haven't run this before, by the way, so this is the first time I'm finding out. Interesting. So I'm actually going over the number of tokens, which means it's attributing a lot of tokens to the model here. So that may be a mistake that I set it to 4,000. Let's just go up and reset that because I don't want that to be the reason for an issue. So I'll reload the model. I don't need to run the images again. Oops. By the way, it's probably best practice to restart the kernel if you're going to reload the model. It'll be fine because the model is small. But really we should have very minimum like delete the model so that we don't mess up the VRAM. Oh, I did the same thing again. Can I get it in time? No, I was too slow. So what I want to do here is block this to 16 and yeah, I mean, I can just do ×4. So yeah, I'm actually going to now delete the model, reload it, and then reduce the token length to 16384, which should be sufficient, I think. And now I'll run evaluation. I do need to reload my data set. And let's see how it does. Now, maybe my query is not good enough. What kind of chess pieces? No, come on, that's good enough. That's good enough a question for it to say what it sees. And interestingly, it doesn't get that right. Standard wooden pieces, black and white pieces, doesn't quite get the pieces. And this one here, a black pawn, a white queen. The queen is a broken off top, leaving the base intact. Therefore, yeah, that's why it's a rook. So yeah, doesn't perform great. 0 shot. I'm not sure if there are any models that perform well 0 shot. Let's take a look though. I know I'm diverging a little bit here, but let's take a look at Florence 2 because I don't remember exactly how that performed. But let's take a look for a comparison. I'm very curious what performance Florence 2 got. And I ran Florence 2 with the large model, so 700 million parameters, so a little bit more than the 500 SmolVLM. And did I run it on chess? I think I did. Yeah, I ran it on chess, but I ran it in a little bit different of a way because I was doing bounding box fine tuning. Now, yeah, this is where I've rerun it after training, and it's, I mean, this is me with data prep, is it? Yeah, I'm just doing data prep here. Now, evaluation before training, yeah, it's not doing well at all. It's getting the pieces. But evaluation after training, let's take a look at how it does then. So a white king, a white bishop, let's score that 1. White pawn, black rook, that's 2. Black bishop, 3. So it's already got 3 correct. Black knight and white rook. So it's gotten 5. And that's with the bounding boxes, which are excellent. So yeah, you can see Florence is getting like 5 out of 7 already. So let's see how well Qwen does. I suppose we can check as well how it does on these dog and cat. That's a bit boring. Let's take a look at this image here, which is the Financial Times. So we're checking here for OCR. Let's see how it does. Yeah, it does pretty well. Farmer's Fury. Big text, tight grip on AGI or AI Revolution. Do we see that? Yeah. Where's it grabbing that from? This one here. It's doing a good job. It's picking out the main big titles. So This is pretty good. Now this is a 3B model, so it should be doing quite a bit better. All right, so next we're going to run the training loop. And yeah, this is the data collator, the standard data collator that will fine tune on all of the tokens, question and answer. But we want to focus on the responses. So we're going to look at this one. And we do need to run it. And notice that the hard-coded subsequence is going to be different. The hard-coded subsequence is going to be, let's see, where is it? Find the sequence. I actually don't initialize it here. So how do I set it? Assistant tokens. And how do I define assistant tokens? I define it as the first token when I tokenize the assistant response. So yeah, this is a different approach. I'm tokenizing the assistant response. And when I do that, the very first token, which I think will be assistant or something like that, is going to be used to identify the start of the assistant sequence, and everything before that is going to be masked. So when I run that, I can inspect the data set. And yeah, it looks to be working because I've got a match between the assistant response and the decoded labels. If this did not match, decoded labels would include some of the question, so I would immediately see that that's not matching. So this looks to be fine. Okay, now there's a snippet here you can start with if you want to do multiple images. I'm just going to run with one image, and I'm going to run the model again. It's got a similar structure. It looks like it's got visual encoder. Then it's got a Qwen 2.5 VLM model, or VL model. This is probably just the text model, the LLM. And it's got what it's called a merger. So it looks like a sandwich. So MLP here, linear, GALU, and then linear. So for Qwen, I'm not going to train absolutely everything. I'm going to train the QKVO up-down gate projections. So these are attention, and up-down and gate. These are from the linear layers. I'll also train MLP 0 and 2. Now, does that make sense in the context of this model? It does. I'm going to train this linear there and this one. And I'm also going to train the language model head and the embedding tokens. Now, why not do all linear? It causes issues with Qwen. I think it's because it picks out one of the linear layers that ends up giving issues. I'm not sure which one it is, but there might be a linear layer that's being picked out that essentially gives issues. I think actually it might try and do something funny here, whereby the GALU gets mixed in. I'm not confident on that, but I do know this gives issues. So we're going to stick with the plan. Notice that the LoRa alpha of 32, that's probably a little bit high for a small model like this. Typically the alpha should be representative of the square root of the hidden dimension. I talk about that in one of my LoRa fine-tuning videos. So I could go with something a bit lower here. Maybe even as low as 8. How low did I go on SmolVLM? Let's see. I went as low as 16. Yeah. And I went for a higher rank because I want to have more parameters that are trainable because it's a small model. So yeah, let's leave it at 16, or let's lower it at 16 because it was higher. So we'll run this and we'll apply the LoRa. And my guess here is this is going to be 10%. That's my guess. Let's see. Maybe a bit less, maybe 7, because the model is bigger. Oh, 15. Okay, fair enough. It's still large because we're training those MLP, we're training the embedding layers. So that's resulting in fully trainable layers. We're not applying adapters. We're actually fully training the embedding layer and the language model head. Okay, so now we're going to do some training, and I am actually going to do this, so you'll get to see how I do it. My learning rate needs to be fairly high because it's a big model. 3E minus 4. For SmolVLM, what did I use? I used 5E minus 3. So here it's 3E minus 4, so it's smaller. That makes sense. Smaller models need to have higher training rates. This is a larger model, so needs a smaller training rate. And I'm just going to train for one epoch at constant, and then I'm going to anneal for a full epoch. And my batch size here, I've got a batch size of 1. Typically, I would like that to be a bit larger. I see a gradient accumulation of 4 on. So I'm going to increase that to 4. It's generally better to increase the batch size to make use of your GPU. It provides averaging across the data as well. although it means that the averaging will kind of ingrain less specific data on each image. So it can go both ways. If sometimes you have a small data set, it is better to train with just a batch size of 1. Now, since I've done gradient accumulation of 4 in SmolVLM, I'm going to keep it the same, like a virtual batch size of 4, but I'll do it by setting it on the batch size side rather than the gradient accumulation side here. Let's rename this and 2.5 VLM. That would be my hub model ID. And yes, this sometimes gives errors if you try and use reentrancy with Qwen. It's a bit annoying that we have to leave it false because it does make the training slower and take up more VRAM, I think. So let's see how it goes. Maybe I'll hit some errors here, or maybe I'll be lucky. I reckon it'll take possibly 5 minutes to train, possibly 10. And we do have an issue. So we're out of memory. And the solution for out of memory is to go back to what we did have, which I now regret. That's okay though. Restart the kernel, go up here, reload the model, reload. Make sure I reset the length of the processor. That's another lever I have for reducing the size of the model. Another lever is actually, so I should have said this, but one of the key things about this Qwen model here in the technical piece is that it allows for a dynamic number of tokens for every image. So if you have a big image, it's going to represent it with a lot of tokens. And if it's small, it's going to represent with a small number. So a small image might be 8 tokens. A big one might be like 11,000 tokens. And the images I have are high res. So that's probably why they're taking up 11,000 or even 15,000. And my context is quite long. So one of my other levers is just to lower the resolution of my images, and that will reduce my VRAM as well. So let's see if I have to get to that. By the way, one other thing here, it's kind of a bit subtle, but well, maybe not so much. This is really trendy now. It just seems to be better. It's being done across, I think Google probably does it for its Gemini models, although I'm not sure they do it for training. I believe they do it for inference. Maybe they do it for training too. DeepSeek in the latest model. If you look at Modern BERT, an embedding model I talked about recently, all of these are using full attention only in certain layers. They might do 8 layers of window attention where it's only, the model is only looking back maybe 4,000 tokens. And then every 8 layers, they'll look back for the full context length. And it turns out this doesn't degrade performance much, but it saves a lot on compute and memory. So anyway, that's a side note. But what I want to say here is that my resolution is very high in the images, and that's probably not helping my case on the VRAM here, because Qwen is going to use very high resolution in order to interpret the images. Okay, so I need to reload my data, and I don't need to run evaluation, but I do need to run the code so I can run the evaluations later. And I don't need to run that manual evaluation. I do need to reload my data set, which is going to be, this is my data collator. Did I load my data set? If I didn't, I'll just load it quickly again. And now I'm going to run my data collator using the response being focused on using the loss focused on the responses. And now I'm ready to apply the LoRa. And now I'm ready, hopefully, to run training without running out of memory. And I can check on RunPod, by the way, to see if we're getting crushed on memory. And it looks like this will slow down my training, the fact that I have to use a larger batch size. And it looks like, again, we have run out of memory. So I have 2 options here. I mean, there's probably more options as well. But one of the options is to just use QLoRa. So let's use QLoRa in order to reduce the VRAM requirements. You know, probably I would argue it's better for me to go and reduce the resolution of the images, and we can write that code if needed. But, and it's possible also, I will anyway need to do that because most of the memory here, a lot of the memory here is probably attributable to the KV cache, possibly, and not to my model. So just by running quantization may not be enough at all to make this work. But we're going to find out. Okay, so I've restarted the kernel and I'm going to now run in quantized form. So I've uncommented here. So I'm running quantized in 4 bits. I'm still going to reduce the tokenizer length. I'm going to load the data set. I won't run evaluation, but I've run the function so I can access it later. I'll run the data collator, apply LoRa. You know, the other angle I have here is to just not train the modules to save. This is also going to save memory. It's probably going to save a lot of memory because it means I'm only training the LoRa's and I'm not training any more of those full embedding layers. And yeah, my trainable parameters have gone from 15 down to 2%. So that's going to help a lot. And now let's see, do we manage to train? Interesting. It looks like my model is split across devices, which is a little bit of a surprise. So what I'm going to do is, I could diagnose that, but I prefer first of all to run without the quantization and actually just run with the smaller LoRa. So that's what I'm going to try first. Evaluation before training. I'm not going to run that. I am going to run the training loop. Just check that my data set is loaded. Yep. Print the model. 1% trainable parameters, hopefully, and run the training. 2% trainable parameters. And maybe this will be enough. And it was not. Now, there is a possibility we can try to use the reentrancy. I don't think this is guaranteed at all. I think it likely will give a different error because I know historically that Qwen have had an issue when trying to run with reentrancy. Reentrancy, by the way, means that if you do gradient checkpointing, which is activation checkpointing, you're basically not storing all of the activations on the way forward. You're recalculating them on the backward pass. There's a way to speed that up by building a graph. So that's called using reentrancy. I mean, this is a very simplified explanation, and using reentrancy therefore improves your speed when you're going to do the recalculation of the activations on the backward pass. So ideally we would like to use that, but typically it tends to give errors. So I'm going to see if I can use it, and I'm going to see if that has any effect on the memory. But I don't have particularly high hopes of this running well using the reentrancy. I think we'll get a different error, and I think we'll end up having to go back and trying to run with images that are of a lower resolution. Yeah, I am getting this gradients will be none warning, which sometimes can indicate that basically none of the parameters have been set as trainable and is a problem. I can check here what's happening. It looks like we're barely squeezing under the memory, and we'll find out now when we see the first training loss. We've hit an out of memory error. Okay, so next what I'm going to do is try and shrink the size of the images. So how do we do that? Well, first of all, restart the kernel. And second of all, we need to resize the images. So let's first of all just load the model, same as usual. I'm not going to use quantization. I'm going to just try and get this running in the standard form. I'm going to load the data set, and I'm going to print it out like this. Train data set. Okay. So we have these images, and let's just feed this into ChatGPT. So here I am in ChatGPT, and I'm going to print, I'm going to tell ChatGPT that I've printed this out here. And I'm going to say, this is my data set. I want to reduce the size of the images by a factor of 4. And yeah, let's see what it gives. By the way, I probably should just feed that in. So I should feed in some information on the size of the images. So they are huge images. They're 3000 by 4000. And they're pill images. So this is good because it just is going to know to use the pill library, which is going to be helpful. And so we can apply this, grab this little code snippet, go to my data set and map these images. Now, don't know why it's given this issue here. So yeah, don't know if it really needs to add in that argument there. Anti-aliasing, I'd have to read about that. Seems like That is not an argument that's needed. So it's given some other Langsos. I need to learn more about images, but it looks like it's mapping, which is good. 48 images. And I guess we could show one of the images as well. But yeah, here we go. Yeah, it does look lower res. So hopefully that has worked. And yeah, I mean, I could run evaluation again, but I'm not going to do that. I'm going to instead focus on getting the training running. So we've got the data collator. We're going to set up LoRa. We're going to keep LoRa focused only on, we're going to keep the training focused on LoRa, not going to train the embedding or the language model head. And now let's see how we do on memory and whether I'm correct, which I may not be, but it does look like I am correct because the memory usage is a lot smaller. Yeah, so yeah, you can see if you kind of 4x that, it's starting to get up to the top. You would think we could have squeezed in, but keep in mind that it's quadratic. I think the memory size of the KV cache, I don't know. I would have thought it's maybe more linear actually, but either way, you can see our loss is falling, which is good. The training loss and the validation loss, so we're in good shape. And we could just run evaluation now, but I'm going to run a linear annealing just to see what goes on here. So just keep that in mind, 1.76. It should restart with a validation loss a bit above that. And then it should fall hopefully somewhere to like 1, which indicates that we're kind of getting a nice smooth ramp down. See, if you train at this constant high rate, you're going to be bouncing around because you're basically forcing the model to update at high speed in different directions. Whereas ideally at the end, you want to slowly ramp the process down so that it smoothly starts to kind of zigzag down to a plateau, hopefully. So yeah, this actually is doing the opposite of what I just said. It's not really annealing. If anything, it's quite a bit worse. Any reason for that? No obvious reason. So yeah, I mean, you could go back and run it without annealing. Empirically, that's just what it is. It's not going in line with what I said. But I'll run the evaluation anyway. And a white pawn and a white rook. Okay, not quite right. A black queen, a black rook, and a white pawn. Okay, it's got one of these correct. It's got the colors correct in all cases so far, though. And then a black knight and a white rook. Okay, so, you know, I'm just curious. I'm just curious if that annealing really messed things up. So let's rerun it. And I'm actually not going to rerun. I'm going to delete the model, like I said earlier, because restarting the kernel will have to run more cells. So instead, I'm going to do this. And by the way, I probably could reduce now the number of tokens because I bet you we're not using that many tokens. So that's another point as well that maybe could. I don't think it would actually make that much difference though, because anyway, the collator should truncate to the longest sequence. So I don't really think that will help doing it. Okay, I've run all of this. I do need to reapply my LoRa. I don't need to reload anything else, but I do need to reapply the LoRa here. Check how many printable parameters I have. And then I said I would just run it with the main fine tuning. Now, based on what I showed you, I'm only training for one epoch here. Maybe you should train for another epoch, especially if you want to be consistent with what I showed in the other earlier model. So you could argue it's a bit unfair. I'm only training for one epoch here, especially when the validation loss is still falling. It indicates that we could train for more. But it's never going to be apples to apples because the learning rates anyway are different for different models. The LoRa is not exactly the same applied. We're not training the embedding layers here. Although we could try and train the embedding layers now. And maybe that might help a little bit. But let's just see how we do on the evaluation. You can see the validation loss this time around. There is a bit of randomness compared to the last time. Hopefully should fall. Yeah. And while we're waiting, something I should say is that to inference these models, you want to use VLLM or SGLang. The libraries should support it soon. and you will be able to find the model if you go to the one-click LLMs folder, repo. Just go to Qwen 2.5 and you should be able to find the VL model here. I'll put it under SGLang as well, but support is not live just yet. I'll put it in the comments in the description once it is. You can see here there's a request in VLLM to support it, and there's a request in SGLang here to support it as well. I'm tracking these issues and I'll update on YouTube when they're ready. But yeah, in the meantime, let's go back to the training. You can see we got to 1.2. How do we perform here? A white bishop and a white knight. Okay, so it got them right there. A black bishop, a white queen, and a black knight. So it's got 1 right, so that's 2. Oh, sorry, no, 3 right so far. And then here a white knight and a white bishop. So that's quite poor actually. So it's still only got 3 right here. So yeah, the other ablations I'd recommend doing, potentially try using the modules here. In fact, we can even, we can't on the fly easily apply another LoRa because we've already applied a LoRa. You'd have to go back and reload the model. But I probably do recommend trying this. I'll put may cause issues for Qwen, but I think you might want to consider using these extra modules to save just to see if they give a little bit extra in terms of the performance. Also, you're thinking about dataset size, optimizing the learning rate. Clearly here, our learning rate, or sorry, our validation loss is still falling. So probably it does make sense to continue training for at least another epoch. In fact, I can just go ahead and train for 1 epoch here now, and I'll run it quickly. Keep in mind, this is just the LoRa. I haven't applied those embed tokens or LM head. So you can see when we run this second epoch, the validation loss has gone from 1.12. I know my text is very small. Sorry, I should have increased this earlier. But my loss has gone from 1.12 back up to 1.42, then 1.58, 1.5. So it's not entirely clear that running this second epoch is actually helping. It may be more of a case we should have started to do some annealing, or perhaps our learning rate is maybe a little bit too high. It's probably not too far off. So white bishop beside a white knight, it's getting that right. A black queen, a white bishop, and a black rook. Okay, it's gotten 2. So that's 1, 2, 3, 4. And the last one, a black knight beside a white king. 5. So yeah, we've gotten some better performance here. We're up to 5 out of 7, which is matching the same as the Florence model, and this is on the 3B model. So I would say this 3B model from Qwen 2.5, it definitely seems a bit stronger than the Qwen 2 VL model, the previous version. Qwen 2 2B, that is. As you go up to the larger ones like the 7B or the 72B, you can get even better performance. So I would recommend, if you want to get the best possible performance, you should repeat the process I've shown and do it on the larger models. Now, I always say when I have clients talk to me in consulting sessions, I always say to them, start with a small model, run through the pipeline, get it working, even with bad performance, before you move to a bigger model. In fact, never jump either, go from the 3 to the 7 and then the 72, because everything you do in the smaller models is multiples, orders of magnitude faster, and you can just iterate and get everything right. And then you'll be able to do everything well. When you move to the larger models, you should just be seeing performance improvements. So that's pretty much it for Qwen. And that rounds up the comparison of all of the models. As I said, Florence 2, even though it's old, it's still a really powerful model for its size. SmolLM, interesting because it's so lightweight. You can run it very easily. In fact, there's this little demo I'll show you to finish off. And then finally, Moondream is a very nice specialty model. It is strong as a model, maybe not as strong as Florence 2 in some applications, but it has that gaze feature, gaze detection. So something to look at as well. So just to wrap things up, I'll show you this demo from Hugging Face. It's a SmolVLM running in the browser. It's not supported because I'm in Safari, but I will open up Brave. So here I have the Brave browser, and I'll go to Hugging Face. Brave or Chrome will support WebGPU. This, if you have a Mac, will connect your GPU, or it will use your CPU. I have tried it on an older Mac, which means, and it was not particularly performant. So unfortunately, I think the way that it leverages a CPU raw is not particularly good. And when I say it's not good, I mean if you ran Llama CPP or some more direct optimized package, you probably would do a lot better. But WebGPU does really well on Mac, or probably if you've got a latest kind of Windows PC. So here we have SmolVLM. Let's load the model. And I'm going to test it out by just passing in an image of one of my YouTube videos, see if it's able to read the captions. Okay, and the Onyx model has been downloaded. And I've just uploaded a copy of an image here. It's one of my thumbnails from one of my videos recently about running reasoning models on laptops. And yeah, how to run reasoning LLMs on any laptop. It does have a typo on it. But this is pretty incredible for a model that's 250 parameters. I think this is pretty good performance. Now, it seems like it won't actually allow me to pass in a follow-on model. So I'll just say, give me a detailed, let's try it again. And this is live, it's not running remotely. The man with a beard is on the poster and it says how to run below. It says rationaling LLMs on any laptop. Okay, so maybe not quite as impressive as I had been letting on, but definitely impressive. I can just kind of get this going quickly and run it here on my laptop. If I use the 500 million parameter model, it would be even stronger. I suspect that running something like Florence 2 might be able to get this a bit better. But anyway, this gives you a sense of the capabilities. So that is it, folks, for this roundup of vision language models. As I said, I'll post an update with the one-click templates for Inference once they go live for Qwen. And in the meantime, let me know of any questions below. Cheers.